Thank you, Magali. It's a pleasure to be here. This morning, I'd like to share with you a bit of work that my PhD student, Lisa Esteves, postdoc Ernst de Muy, and I have been doing in the recent months to do with using Kepler Photometry to measure phase curves of a number of close-in exoplanets. As you know, Kepler was designed to be a transit machine, but the high cadence, the high precision, and the continuity of the observations mean that the Kepler data are ideal for measuring phase variations of exoplanets throughout their orbits, not just when they are passing in front of the stars. Already a number of groups have published phase curves for individual hot Jupiters and for small samples over the last few years, including ourselves last year, and for two super Earths that are relatively bright and hot and close in, and therefore measurable through their phase variations. Of course, with a single broadband filter in the optical, it's not possible to fully disentangle the reflected light component from the thermal emission contributing to the phase variations. On the other hand, with Spitzer measurements that have been done over a number of years now, which focus on measuring the thermal emission in particular, it's been possible to make direct measurements of day-night contrast, for example, to in some cases even identify offsets of thermal emission hotspots from the substellar point in some planets. Just last year, De Mori et al. Published a very interesting study of Kepler 7b combining both Kepler and Spitzer data, and they were able to make a case that there is an offset in the peak of the planet's phase curve from the substellar point, which might be suggestive of reflective clouds inhomogeneously distributed across the longitudes of that particular planet. And that the Kepler band light, the Kepler band emission in that case is dominated by reflected light rather than thermal emission. As you probably know, a phase curve is a combination of three different independent phenomena. The light from the planet itself, which is a combination of reflected light as well as thermal emission. If I could find the pointer here, maybe not. Contribute obviously to the phase variation, and that depends on the albedo of the planet, the temperature, and the heat distribution between the day and night sides of that planet. Secondly, there are the ellipsoidal variations, which are effectively fluctuations in the star's visible surface area as the stellar tide caused by the planet rotates in and out of our field of view. And thirdly, there are the Doppler beaming. There's the Doppler beaming contribution, which is the boosting resulting from the reflex motion of the star as the planet orbits it. What we've done over the last several months is to conduct a comprehensive analysis of phase variations of Kepler planets, of all Kepler planets and planet candidates that have been published with periods shorter than 5 days. So we basically tried to comprehensively search the entire database of 18 quarters of data available publicly now to look for phase curves. So we basically take both the long cadence and the short cadence data, the simple aperture data, and fit co-trending basis vectors, as many of you I'm sure are familiar with, to correct for the instrumental effects, then normalize each quarter to its out-of-transit median to remove quarter-to-quarter discontinuities, and then remove any 5 sigma outliers by calculating a running median and a sigma. So here are some of the examples. We basically model the full phase curve simultaneously, including the primary and the secondary transits, and therefore we can derive albedos, day and night side temperatures, and planetary masses. Most of the planets in this sample, the 14 where we do see significant phase variations, have low geometric albedos with a few exceptions. Here are some of the examples, and a few more here, including the phase curve for the hot super Earth Kepler 10b in the middle there. Of the 14 planets that we fit, all but one favor a perfectly circular orbit. The one exception is KOI-13b, where a very small eccentricity on the order of a few times 10 to the minus 4 seems favored over a perfectly circular orbit. That's the only exception. One of the more intriguing results from our study so far is that there seems to be 7 of the 14 targets, about half of our sample, suggests that there is an offset between the peak of the planetary light and from the mid-eclipse or from the substellar point. And interestingly, or intriguingly at least, the 5 cooler planets at the bottom of the diagram there tend to show a westward shift or shift to the morning side of the planet that's coming into your view. And the 2 hottest planets in the sample with effective temperatures, equilibrium temperatures greater than about 2500 Kelvin show eastward shift, so in the opposite direction to the evening side of the planet. What could this mean? The westward shift, at least for a tidally locked planet, as I mentioned, would imply that it's brightest on the morning side. It's coming after the eclipse. For the hottest planets, what we're seeing is, for the hottest planets, what we're seeing is an eastward shift or to a before eclipse in this particular case. It might be that this is a plausible explanation if this really holds as a trend. It might be suggestive of, in one case, inhomogeneous clouds dominating the emission. In other words, for the reflected light dominated cases, it may be that the planets are cool enough that particles could condense and form clouds on the morning side, and these clouds are peaking as the morning side comes into view and disperse gradually through the rest of the day as the planet's atmosphere heats up. At least it makes for an interesting story. And for the hottest planets, where the temperatures may be too hot for the particles to condense, the brightness may well be dominated by the thermal emission. Assuming these are tidally locked, then the eastward shifts are in fact predicted by some of the circulation models that are out there, suggesting that there may be winds that are moving in the direction of the planet motion, and therefore you would expect an eastward shift for the peak emission in the case of thermal emission dominated planets. There are a number of other interesting things we see in the sample. 2 of these planets are known to have asymmetric transits, KOI13b and HAT-P7b. This may well be because of significant misalignments between the stellar spin and the orbits of these planets. These same two planets, we see significant out-of-phase variations. In particular, we see out-of-phase variations that are in the phase curve residual that are at a third of the planet's orbital period. So this residual third harmonic may again result from the spin-orbit misalignment in the case of these 2 planets. There are many interesting details in the study that you'll have to wait for the paper to see. But of the 14 planets, we've reported now a large increase in the population of Kepler planets with phase curves reported, and that therefore we report albedos, day-night temperatures, and planet masses for these. Most, as I said, have low geometric albedos. Only one case we do see a preference for a slightly eccentric orbit. The third harmonics are seen for the first time in 2 hot Jupiter planets, which may be the result of spin-orbit misalignment. The most intriguing bit of the study is, as I said, is that there may be a possible correlation between the peak of the planetary light and the equilibrium temperature of a planet. Whether this holds with a larger sample is yet to be known. I should mention a word of caution. We also did a bootstrap analysis of the data in order to compare to the errors that we get from the Markov chain Monte Carlo analysis. And the caution is that we do find that there are residual systematic and/or stellar variation effects that are often not counted for in the errors that people report in the MC fitting. So that's something to be aware of and be cautious of. So I'll end there. Thank you.
What about the planets that show no peak offset? Are they the same temperature range as, are they high or low temperature, or where the third category?
Yeah, that's a good question. We should have actually plotted that on here. So basically what we're doing is that for 7 of them, there's no offset favored in the fitting, right? So you don't need to include an offset to get the best fits. They do span quite a range of temperature, for sure. In some cases, there's a bit of uncertainty. The uncertainties are a little bit larger, so it's not quite as easy to tell, but I apologize that I should have plotted those here in a different color maybe so you could see clearly.
Does that mean they show no offset at all, or are they just also consistent with 0?
They're consistent with 0. That's what it is. Yeah. Hi. That's an interesting question. It's the next harmonic that we would see, right? So that's basically, we're seeing a residual, sorry? Not sure. Yeah, it's already included in the fit, right? So the next residual that's left is well fit with a third of the planet period. Does that make sense? Yeah.
There's a question
Yes.
here, Isabel.
Hi, Ricky. The correlation you find with the peak offset and equilibrium temperature, do you have also information on the gravity of those planets? Do you have actually the mass for them?
So, yeah, do we have information about the gravity of the planet?
Yeah, and just to see whether there would be also correlation with gravity. You'll see in my talk I mentioned something about that. Yeah.
Okay, so we do have some constraint on the gravity from the photometry alone, because we can have some constraint from the ellipsoidal variation fitting and the Doppler boosting, right? But not in all cases are those masses very well constrained just because of the uncertainties in the data and the fit. In a number of these cases, obviously, there's radio velocity follow-up. So there are some constraints on the masses of a subset of these planets. I'm not sure that I'm trying to think if we have a way of, there's no direct measurement of gravity, but I guess in principle you could look for correlations with mass.
That would be nice.
Yeah.
Further on KORoT3, I was the last author on the Sabo et al. Paper, so I was the team leader in that group. So we found in other paper evidence for a 5-to-3 spin rotation resonance in that star. Do you see any confirmation or confirming pieces of evidence of that your models somehow, extract that information? There is a spin orbit resonance of the planet and the star.
Whether we in the photometry alone, whether we see the
or in your models. I mean, this slight eccentricity is interesting. I mean.
Yeah, I don't think we do, but we can look into that. Yes. So you found that from the photometricans. Okay. Okay.
Follow up on the third harmonic question. The current model for beaming Doppler, for beaming ellipsoidal variations and so on are sinusoidal, whereas the true emission of a sphere is not sinusoidal. If you indeed see the third harmonic and so on, can you disentangle or try to constrain the true Lambertian or other emission model for the sphere?
So we did try 2 different sets, and it seems pretty much, I guess the uncertainties in the data are such that we can't do a whole lot better at the moment. So, but that's something to definitely to look into for these 2 particular cases. I mean, we see the third harmonic in 2 particular cases, right? So we need to, we can look into that. Yeah, thank you. Good point.
On this graph that you have here right now, have you made an estimate, or do you know which ones of the planets are tightly locked and which ones could be expected to be rotating independently of the star?
Well, so all of these planets have orbital periods shorter than 5 days. That was a selection criterion in our study to begin with. So the assumption is that they're all tightly locked. That's what we took to be the case, but we don't have an independent way of testing that.
Right.